Howdy, howdy. This is Mr. Potter. In this last section of chapter 3, we're, we're going to kind of round out what we've been trying to achieve in this chapter. This chapter has really been dealing with derivatives. And whether we've been talking about polynomial functions, rational functions, compositions of functions, trigonometric functions, or inverse functions, we've been talking about how do we take the derivative of all of these functions that we've been learning through all of the math courses up to and through pre-calculus. And today we're going to flesh out that library by taking a look at exponential functions and logarithmic functions and trying to determine their derivatives. So we're going to start with a very interesting limit. I want to take a look at e to the x minus 1 over x. So I'm going to take a look at this function. I'm going to graph e to the x minus 1 all divided by x. And I want to take a look at the graph for this function. And of course, one of the first things that I notice is that this looks an awful lot like an exponential function. And when we get to chapter 9, we'll be talking about why this looks so much like an exponential function. But I really want to take a look at what's happening here, right about here, right where x equals 0. So if I go to my trace, I notice, of course, that it's undefined at zeros, but for values very close to 0, the graph appears to be passing through the point 0, 1. So it appears that the limit as h approaches 0, or as x approaches 0, of this function equals 1. And this actually helps us with the idea of coming up with the derivative of an exponential. So if I want to take the derivative of e to the x, and I want to do this straight by the definition of the derivative. Remember, the definition of the derivative is the limit as h approaches 0 of e to the x plus h minus e to the x over h. And so starting with this, I know that I can factor e to the x out, because this term here, because of the property of exponents, this is really e to the x times e to the h. And so I can factor e to the x out as a common term. I've got the limit as x as h approaches 0 of e to the x times e to the h minus, well, e to the x times 1 would give me my e to the x back over h. And from the property of limits, I know that I can just take this e to the x out, because it has nothing to do with h. So it's going to be e to the x times the limit as h approaches 0 of e to the x minus 1 over h, which we just talked about. We said that that limit appeared to be 1. So what we've got here is we've got e to the x times 1. And so this brings a rather novel idea that if I want to take the derivative of an exponential function, I end up with the self-same function, e to the x. And so this brings to us a very interesting idea. The derivative of e to the x is e to the x. And of course, this really means that when we're taking derivatives of expressions involving exponentials, they're quite easy to work with. If I want to take the derivative of e to the x squared, well, here I've got f is e to the u, where u is x squared. So I can take the derivative using the chain rule. I should have e to the u times the derivative of u, or 2x times e to the x squared, because multiplication is commutative. I could even do a function like e to the sine x power and take its derivative. And so what I've got here is my derivative should be e to the sine x times the derivative of u cosine x. So the fact that the derivative of the exponential function is the exponential function really does allow me to take these derivatives quite quickly. Now, the one caveat is that our base has to be e, the natural log base. So the question naturally arises, what if I'm dealing with exponential functions with a different base, such as 2 to the x or 3 to the x? If I'm dealing with half-life, I'm going to be dealing with 1/2 to the x. If I'm going to be dealing with a lot of the common log problems, or if I'm dealing with I'm going to be dealing with 10 to the x quite a bit. So how do I deal with these situations where my base isn't e? So if I have that situation where y equals 2 to the x, for example, I know that this is really the same function, that the natural log of y would be equal to the natural log of 2 to the x. And one of the properties of logarithms is that if I have an exponent inside the argument of my log, it really can come out to in front of my log. So this is really equal to x times the natural log of 2. So if the natural log of y equals the natural log of 2 times x, I can take the exponentiation of both sides. And so y is really equal to e to the x times ln 2. And ln 2 is a constant. So if I want to take the derivative of this, the derivative of an exponential function is that exponential function times the derivative of this exponent. Well, the derivative of a number times x is just that number. And so what we notice is in general, if I want to take the derivative of a to the x, where a is any number, that's going to be equal to a to the x times the natural log of a. So this is the rule if I want to talk about any exponential, not just a base of e, but any base. The derivative of an exponential function with a base of a is equal to that same exponential function times the natural log of a. And of course, in the special case where a is e, I'm really dealing with e to the x times the natural log of e, but the natural log of e is 1. So I want to go through a couple of examples of these. So let's say that I've got y equals 3 to the radical x power. Of course, realize that when I'm talking about square root of x, that's really 3 times x to the 1/2 power, and I can use the power rule when I take its derivative. So the derivative of an exponential is a to the u power times the natural log of a times the derivative of u, which in this case would be 1/2 x to the negative 1/2. Now, I may see this as 3 to the radical x times the natural log of 3 over 2 times the square root of x. That's one way I may see this derivative written in a more concise form rather than just in a long line of multiplied terms. I could just as easily take a look at the function y equals 5 to the tan inverse x power. And of course, I know the derivative of tan inverse from what we just talked about was 1 over 1 plus x squared. So the derivative of an exponential is that exponential function times the natural log of my base times the derivative of my exponent. In this case, the derivative tan x would be 1 over 1 plus x squared. And so what I find now is this is really 5 to the tan inverse x times the natural log of 5 over 1 plus x squared. And so this rule, as a matter of fact, this one limit that we had, that the limit as h approaches 0 of e to the h minus 1 over h, the fact that that limit is equal to 1 really does help us to blossom out all of these exponential rules. And the rules for taking the derivative of an exponential function are very, very simple. So that means that we should be able to use inverse functions to talk about y equals the natural log of x. Because if y equals the natural log of x, that certainly means that e to the y should be equal to e to the natural log of x, or just plain old x. And if I wanted to take the derivative of this expression, e to the y equals x, well, the derivative of x is 1. And anytime I take the derivative of something involving y, I'm going to get dy dx coming out of that. And so I can solve for dy dx. So dy dx in this case is 1 over e to the x, which we recognize this from inverse functions. Our derivatives of inverse functions tend to be 1 over the derivative of the function. But the derivative of e to the y is e to the y. But I know that everywhere I see an e to the y, I can replace it with x. And so what I've got here is I've got the derivative of the natural log function is equal to 1 over x. And so this gives us another relatively simple way to take derivatives. And just like when we were dealing with the trig inverse functions, we're taking a function that on its surface seems very, very complicated, and in the act of taking the derivative, it actually seems to simplify. It just turns into a rational function. So I can go through a couple of examples here. And the first example I want to do is I want to take a look at the natural log of x cubed. And I want to take the derivative 2 ways. The first way I'm going to do it is just by using the chain rule. The derivative of natural log of u is 1 over u times the derivative of u. So the derivative of x cubed is 3x squared. And of course, if I was to simplify this, I actually end up with 3 over x. But I want to do this a different way, because I know that the natural log of anything with an exponent, I can bring that exponent out. So the derivative of this function really should be equal to the derivative of 3 times ln x. And now 3 is a constant. So I'm going to end up with 3 times the derivative of natural log of x, which is 1 over x. And notice that that's equal to the derivative that we got using the chain rule. So if I do a little simplification at the beginning, sometimes I'll end up with a much easier function that I have to take the derivative of. One more example of this. Let's say that I've got the natural log of cosecant x. Now I want to take the derivative of that function. Well, the derivative of natural log of u says it should be 1 over u times the derivative of u. Well, the derivative of cosecant is negative cosecant x cotangent x. And I'm just doing a little bit of simplification here. I know that my cosecant terms will divide out, and so I'll be left with negative cotangent of x. So I've got an expression where the derivative of this function actually comes out to be fairly simple. So what I can do now is I can take a look at situations where I've got not just the natural log, but the log base 10 of a function. So let's say that y equals this natural log base 10 of a function. Well, I know that the change of base rules that we learned in pre-calculus says this should be equal to the natural log of x over the natural log of 10. And natural log of 10 is a constant. So if y is really equal to this constant times natural log of x, if I want to take the derivative, it should be equal to that same constant times 1 over x. And so what we notice is that if I want to take the derivative of y equals the log base a of x, it's going to be equal to 1 over x times the natural log of a. And I see the similarity to when I was taking the derivative of an exponential a to the x. I ended up multiplying by the natural log of a. When I'm taking the derivative of these logarithms of base a, I'm going to end up dividing by natural log of a, because multiplication and derivatives, because multiplication and division are inverse operations, just like exponentiation and logarithms. So let's do one more example of this. Let's say that I want to take the y equals the log base 2 of x squared plus 1. So the derivative of this should be 1 over my argument times 1 over the natural log of 2 times the derivative of u, which in this case would be 2x. So I end up with 2x over x squared plus 1 times the natural log of 2. And so that's how I'm finding my derivatives when I'm dealing with non-natural logs. So once again, this is Mr. Potter. Thank you for watching. Have a great day.